So here we have the second example from lecture, and we went over part of this in class, but we didn't finish it completely, and I'd like to go into a little bit more detail on it. So oftentimes we're going to have either two or more vectors, let's say, and we want to find the resultant for them, and the kind of properties or the characteristics of that resultant that we need to figure out would be, well, what's the representation, either in Cartesian or in scalar notation. We also want to know for that vector what's the magnitude is very important, and also what's the direction. Again, the Cartesian notation implicitly gives information about magnitude and direction, but we often want to get the actual scalar magnitude and then the direction in terms of angle versus one or all three of the axes. And again, this is a three-dimensional problem. Everything that we do in this problem will be applicable to a two-dimensional problem. You would just simply ignore everything related to the z-axis if you had an xy coplanar type problem. So here we're given a three-dimensional Cartesian coordinate system. We can double check that we have a right-handed coordinate system. There's kind of two different ways to do that. One way is to put your thumb on your right hand in the direction of the z-axis, the positive z-axis, and x, y, and z are all shown in their positive sense here. I put dashes on the side of the axis that's negative. So here, if I put my thumb of my right hand in the direction of the positive z-axis, my fingers, as I curl them towards my palm, should go from the positive x to the positive y-axis, and that's what happens here. Positive z, I start out with positive x, and as I curl towards my palm, I should be curling towards the positive y-axis, not the negative y-axis. The other way to make sure it's a right-handed coordinate system, and the way that I'm used to doing it, is that you use thumb, index, and middle finger on your right hand. You put your thumb in the direction of the positive x. You put your index finger in the direction of the positive y. And then your middle finger, if you point it out away from your palm, will point in the positive z direction. Either way will work just fine. So here what we're tasked with trying to find is the equation of the resultant vector, the magnitude of the resultant vector, as well as the direction in terms of angle from each of the axes of the resultant vector. So the first thing that we could do is we could just get an idea of what the resultant vector is going to look like in general terms. I've tried to draw this out to scale. It's probably not perfect, but we'll get a general idea of where this resultant vector is going to end up. So even though it's three dimensions and we have an isometric type view here, I could do the parallelogram rule or triangle rule and try to get a general idea of where it's going to end up. So again, we've got, I forgot to label these, we've got two force vectors. Here's F1. The Cartesian notation is provided over there. Here's force 2, F2. And again, it's provided over there in Cartesian notation as well. So I'm going to go from the end of the F1 vector. I'm going to draw a line that's parallel to this F2 vector. And so there's the line parallel to the F2 vector, at least as close as I can get it. And then from the end of the F2 vector, I will draw a line parallel to the F1 vector. And that's, again, as close as I can do it here without looking really goofy. Okay, so where those two lines intersect, that's relatively good art, but I'm not an art instructor, so give me a break. But where the two lines intersect will be the head of the resultant vector. So from the origin, from where both the force vectors start to where the parallelogram rule shows us that it ends, this will be the resultant vector. And so the magnitude of that resultant vector we're going to figure out based off the Pythagorean theorem applied to three dimensions. So we're going to know that the magnitude of this resultant will be equal to radical, whatever component we have in the x direction squared, plus whatever magnitude we have in the y direction squared, plus whatever magnitude we have in the z direction squared. right? The square root of the sum of the squares is going to give us the magnitude of that resultant vector. Likewise, there's going to be some direction that we need to determine as well, too. And so there are multiple different angles that we could calculate. Sometimes you'll see that there's an angle that's calculated in the xy plane. If I were to drop a vertical line down into the xy plane, wherever that ends up from the head of the vector down here, we would measure the angle between the x and the y axis. That's one way to do it. A common way to do it, and probably the easiest calculation to do, is to simply measure the angle relative to each of the axes here. And so the angle relative to the x-axis we call alpha. And so simply, whatever angle is formed between the x-axis and this resultant vector, we call that alpha. We can calculate that relatively easily. Likewise, the angle between r and the y-axis, we call beta. And then the angle between the z-axis and the resultant vector, we call gamma. All right, alpha, beta, gamma, just the first three Greek letters to make it as simple as possible. All right, so we need to calculate the magnitude of the resultant, and we need to calculate the angles alpha, beta, and gamma. And we already have the formula up there for the resultant. But again, the way that we need to figure out the component in the x direction, the magnitude of the component in the y, and the magnitude of the component in the z direction. And so the nice thing is that for vector addition, if you already have it in Cartesian notation, it's very simple. All that you have to do is add up the coefficients or the magnitudes for each of these unit vectors. So I, j, and k, remember, those are unit vectors. And I can even draw those on here just to keep them in mind. I is a unit vector that's pointed only in the positive x direction. All right, so a unit vector has a magnitude of 1. The j unit vector has a magnitude of 1. It's pointed in the positive y direction. And the k unit vector has a magnitude of 1 and is pointed in the positive z direction. So this 50 in front of I, that simply means that it's a magnitude of 50 pointed in the x direction. Minus 100 means that for this vector, the component in the y direction has a magnitude of negative 100. And we can see that makes sense because we're on the negative y side of the origin. And then positive 100k means the magnitude in the vertical direction, the positive z direction, is 100. So each of these scalar coefficients out here, we can simply add up from each of the vectors what those scalar multipliers are to result in our final resultant vector in Cartesian notation. And again, one thing to keep in mind is that here, this vector, f1, only exists in the y-z plane. And so there's only two components to the Cartesian notation, a j component and a k component. But all that we're doing is we're ignoring the I component because the coefficient is simply 0. So this is, if we're trying to be as verbose as possible, this is simply 0 times I plus 60 times j plus 80 times k. We just ignored, or at least the book did when they gave you the Cartesian notation, they just ignored the coefficient, or they ignored the entire first term. So here, if we want to calculate the vector form of that resultant, so r, and I'll put a line on top to recognize we're talking about vectors, not scalars, r is equal to f1 plus f2. So that's going to be the coefficients of I, which is 0 and positive 50. So that's going to be 0 plus positive 50 times I. And then plus the addition of the j term, so positive 60 and negative 100. Positive 60 plus negative 100. That's in the j direction, plus 80 is the coefficient of the k, and positive 100 over here. So 80 plus 100, that's in the k direction. So here I just simplify the terms in the parentheses here, and I simply get that my resultant vector in Cartesian notation is 50i minus 40j plus 180k. So that's the Cartesian notation of this resultant. And if we drew this sketch relatively to scale, we could double check that it makes sense, at least that the resultant appears to have the correct relative magnitude and signs here. So if I were to draw, let's say, a vertical line coming down here from the tip of the resultant vector, again, it's tough to tell exactly, but it looks like it's on the positive x side wherever it would hit this xy plane. It looks like it's on the positive x side, and I have a positive coefficient here. Yeah, I guess so here, based off this, it would actually tell us that it would stop a little bit on the negative y side of things, so it makes it sound like the point would be over here, negative 40, and that the tip here is on the positive z side, which it clearly is. So if I were to project this down to the xy plane, it looks like I have a positive x component, a negative y component. It seems reasonable based off this chart that that's the case, right? If we ended up with some point or some vector over here, we would know that there's something wrong either with the addition or we drew things wrong on our sketch. Okay, so we've got the Cartesian notation for the resultant. That was relatively straightforward. It's just some simple arithmetic. And now we need to figure out the magnitude of the resultant. So we have the equation up there to calculate the magnitude of the resultant based off the Pythagorean theorem. So here, I'll move the work over here. We're going to look for magnitude. So again, the magnitude of r is going to be the square root of the sum of the squares. So f of x squared plus fy squared plus fz squared. The magnitudes of that vector, resultant vector in each of the x, y, and z directions. And so 50 is simply the magnitude in the x, negative 40 is the magnitude in the y, and 180 is the magnitude in the z. So I can just plug in those values, and we have 50 squared plus negative 40 squared. And again, you'll notice that because we're putting everything squared, the signs actually don't make a difference, but I'll include it in there to be complete. And 180 squared, the radical of all of that. And we'll find that the magnitude is 191. So r equals 191. In this case, we're talking about pound force, or the given units for this problem. I didn't include that at the beginning. So magnitude, Pythagorean theorem, relatively straightforward. Okay, so the next thing that we're trying to find, actually another thing we could probably draw on this chart that might help things out a little bit, is I could draw the components of each of this resultant in the x, the y, and the z direction. So in this case, we're going to have some component of this resultant vector in the x direction. I'll call that f of x. We're going to have some component parallel to the y-axis. I'll call that f sub y. And that's, again, in the negative direction. That's why we have negative 40. Here's a coefficient of j. And finally, there's going to be some component all the way up here in the z direction. And again, that's positive. So in this case, you can see that these angles, for example, alpha right here, alpha is the angle between this f of x component and the resultant r vector. And so alpha, I could essentially turn this into a right triangle if I wanted to, where the right angle is right here on this corner. And so r would be like the hypotenuse, x would be like the adjacent side to this alpha angle. And so we can get a cosine relationship. It's the same exact thing over here with beta. It's just that beta here is shown on the right-hand side instead of over here on the left-hand side. But this angle, alpha, beta, gamma, simply represents the angle between the component of the vector parallel to that axis and the resultant vector itself. And so we can use simple trigonometry with that cosine identity to calculate the directions here. So in terms of direction, there's a couple of different ways that we can look at this. So we know, for example, that the resultant vector r, the magnitude of that, times the cosine of alpha equals the component of that resultant. And I said f of x, I guess r of x would be maybe a bit more appropriate. Equals that component in the x direction. And so I could simply rewrite this. I could divide both sides by r, and I could take the inverse cosine, and I would say that alpha equals the inverse cosine of the magnitude of the resultant in the x direction divided by the magnitude of the resultant overall. And we already have the magnitude of the resultant in the x direction is 50, so this equals inverse cosine of 50 divided by 191. And these are in pound force, but the units cancel out. And we get that alpha is equal to 74.8. degrees. And so this is equal to alpha. Likewise, if I want to find the angle beta, beta is going to be equal to the inverse cosine of whatever component of that resultant vector is in the y direction divided by the magnitude of the resultant. And in this case, again, the component in the y direction is negative 40 pounds. And the magnitude of the resultant overall is 191 that we calculated earlier. And so I get this angle. You're going to get two different answers for this, but we know that our vector here is on the left-hand side of the z-axis. It's a negative y, and so beta is measured from the positive y all the way over past 90 degrees and going over. The only answer that's going to make any sense is the answer that's above 90 degrees, and it happens to be 102 degrees. So this is equal to beta. And finally, we do the same exact calculation for gamma. It's just that the component of the resultant in the z direction is 180. So we get that gamma is equal to the inverse cosine of 180 divided by 191. And we get that angle then means that gamma is equal to 19.6 degrees. Okay, so we have the magnitude. Now we have the direction as defined by the angle between the resultant vector and the x, y, and z axes. One thing I do want to point out is that we've already dealt with unit vectors before. It's part of our Cartesian notation. We know that a unit vector, in this case, for I, j, and k, the magnitude is 1. That's the only definition of a unit vector, is that the magnitude is 1. These are special unit vectors because they're pointed parallel to the axes. But you can make a unit vector in any direction that you want to. And in fact, the way to make a unit vector is to take the vector itself and divide it by the scalar magnitude of the vector. And so we already know what the magnitude is. We already know that the magnitude, well, so here if I wanted to get a unit vector in the direction of that resultant, I would simply just have to take the resultant vector itself and divide it by its own magnitude. And that's going to give me a unit vector because I know the magnitude of this is 191. If I divide it by 191, I'll get a vector that has a magnitude of 1. All right, so in other words, all that I'm doing here is I'm taking this, dividing it by 191. So I'll get 50i minus 40j plus 180k, and I'm dividing the entire thing by 191. Okay, so dividing by a scalar is the same thing as multiplying times 1 divided by the scalar, right? This is the inverse of multiplication. And so here, this will look like 50 divided by 191i minus 40 divided by 191j plus 180 divided by 191k. And so the result, that unit vector in the r direction, and again this is still a vector so I'll put a line on top of it, the unit vector that we get is 0.2617i minus 0.2094j plus 0.9422k. And so this vector u, I'm kind of running out of colors here, but I'm going to draw it in blue. The unit vector u sub r is in the same exact direction as r, but it has a magnitude of just 1. And so the advantage of that, the advantage of creating a unit vector in the direction of your resultant, is that this coefficient here, remember this is simply 50 divided by 191. In other words, this is the cosine of alpha, that coefficient. And that's how we calculated alpha before, is we just took the inverse cosine of that number. Likewise, this term, the negative 0.2094, that's the cosine of beta. And 0.9422, positive 0.9422, is simply the cosine of gamma. So it's another way to get to the same exact answer. It's just that now you also have it in unit vector form as well too. Either way is fine. I mean, again, it's just how you organize your calculations. Either way is fine. So now we have the resultant vector graphically. It's a good approximation if we draw it as close to scale as we can. Again, using a ruler, labeling our figure. We have the magnitude based off the Pythagorean theorem. Square root of the sum of the squares. And once we have that, then we can calculate the direction based off the angle between the resultant and any axis that we want. So keep in mind, if this was a two-dimensional, a coplanar type problem, we could use the same exact equations, except that we're just going to get, we're going to erase one of these magnitudes because one of these will be 0. So the most common we would see is an xy plane. Everything fz related would just be equal to 0. All right, so for example here, for the angle gamma, cosine of 0 divided by whatever the magnitude is, let's say 191, it'll give us 90 degrees, right? So we just know that it's going to be perpendicular to that z-axis because the cosine of inverse cosine of 0 is just 90 degrees.